everyone. In the last few lectures, we have been discussing about the borehole environment, such as we discussed different concepts. For example, mud filter invasion, what are the flush zone, transition zone, invaded zone, what is the resistivity profile, how to calculate the mud resistivity and the filtered resistivity and the mud cake resistivity at reservoir temperature and pressure conditions. So the borehole condition is very important to evaluate because it is going to affect our wireline log reading. So for example, we'll start today with the first wireline logging tool, that is the registry logging tool. So registry logging tool, which is going to measure the formation resistivity, we can be affected by the mud cake, flush zone and invaded zone as well as the surrounding bed resistivity. So since we have already understood the borehole environment, it will be easier for you to understand what is what will be the log reading from a ratio logging tool that you run in the well bore, and how to use that log reading to get the true formation resistivity and then calculate the formation water saturation. So let's start the lecture. Today lecture will be about to give you an introduction of ratio logging tools, what are different type of ratio logging tools, how they work. We will discuss some quantitative as well as qualitative application examples, such as using saturation equations or the Archie equation to calculate the formation water saturation. Once we have formation water saturation, we can calculate the oil water saturation, and we can also calculate the initial oil and gas in place. So let us first understand what are the different factors which can affect the resistivity of the formation. Now we should make it clear that first that RW is the formation water resistivity and the rock resistivity is different from the formation water resistivity. So RW is resistivity of our formation water, where RT is the term it is used to define the resistivity of the formation rock. So for example, here what we have a cube of formation water. Let's say all these three cubes have equal dimension. This is a cube of formation water which have a resistivity of RW. Now, when you're moving from this cube, here we see the porosity is 100%. That means we have 100% pore volume in this cube. There is no rock, and saturation is 100%. So it is essentially a cube of formation water. But this cube, the porosity is 20%. That means now rock in this cube, rock material is or rock matrix is 80%, and the pore volume is only the 20% part. But saturation is still 100%. So pore volume, this 20% pore volume have what? 100% formation water. So this rock can still conduct electricity. Why it can conduct electricity? Because it has still the formation water. Now going from this cube to this cube is different, is that we have introduced additional element, that is a rock matrix, that is solid part. Now the solid part of the rock does not conduct any electricity. A solid part of any sedimentary reservoir rock does not conduct any electricity. The sandstone or carbonate such as limestone or dolomite, they do not have current carrying capacity. They are totally non-conductive rock. That means here, even in this cube, electricity will still be conducted by what? Our formation water, which is occupied in the 20% pore volume part. Now compare the resistivity of this cube and this cube. This cube have what? The first cube had what? 100% formation water. Obviously it will have higher amount of ions compared to the second cube, which have only formation water in the pore volume. Formation water amount is decreased, so number of ions which can conduct electricity in the formation water have also decreased. So obviously this rock will have higher resistivity. You can see the resistivity is increasing. So obviously that means what we can see, that for the same dimension formation rock and formation cube of formation water, formation rock will have overall high resistivity. So resistivity of rock is higher compared to the formation water resistivity it contains. Another thing that need to be considered is that, like here electricity can flow like this in a straight path, you can say. But in a rock, the path are tortuous. The current have to take a separate path. So like current have to flow like this, because the pore spaces, the pore channels, they are not straight. So current have to travel a larger distance. That will also cause the resistivity of the rock to increase. So this, since the rock is tortuous, the current is have to follow tortuous path. So again, rock will also have higher resistivity. Resistivity will increase. So a residual rock which is completely saturated by formation of water is denoted by R. Now, if you mix another changes, now property is same, but saturation of water have decreased from 100% to 20%, and saturation of hydrocarbon we have increased to 80% from 0%. So now the pore volume which are earlier occupied by all 20% pore volume which were earlier occupied by formation water only, but now in this rock pore volume is occupied by both hydrocarbon and formation water. So what we are doing when in oil bearing zone, what we are taking it out, formation water, adding more oil or more gas. And again, oil and gas is totally non-conductive. So whatever the conductivity in this rock will be due to only the presence of chlorinated water. And compared to the first two cube, since now we have increased the oil saturation, the amount of chlorinated water saturation will be less than the this cube and the first cube. So this way what will happen is that the amount of iron which is there inside this rock is less, so its conductivity will further decrease or resistivity will increase. This third cube will have the higher resistivity. So now we can compare. A formation water has certain conductivity. A rock which which have only formation water 100% saturation, it will also have certain conductivity, but its conductivity will be less than the its conductivity of the pure formation water. And rock which have oil also, it will have the highest resistivity or lowest conductivity. So in all this case, what is the things responsible for the flow of current? That is the formation water, because it contains the ions for the current to flow. So to summarize all this concept, a reservoir can carry the current because the salinity of formation water. A fresh water bearing formation which does not have any salt, thus it does not have any oil, it cannot conduct any electricity. It also depends upon saturation and type of fluid. So what is saturation of fluid? So if we have higher water saturation, that means more amount of formation water in the rock, and thus you will have what? More current capacity. So if the formation water saturation is high, the resistivity of the rock will be less. Porosity of the formation. Porosity means what? High porosity means what? High pore volume. This means what? Volume of water will be high. That means more ions for current to flow, and that means less resistivity or high conductivity. Then degree of cementation. So basically, how tortuous path is that? I mentioned that like in this first cube, the current have to make going a straight path, but the tortuosity part will be defined by the tortuosity factor A, also as a cementation factor M. So that will define if the current have to take a larger path, the resistivity of the rock will increase. Then lithology of the formation. For example, lithology of the formation, sandstone, limestone, and dolomite, which are the reservoir rock, they do not conduct any electricity. But some clays can conduct electricity because the clay has some bound water inside them. The clay can also allow the movement of ions through their structure. So if you see shelly formation, they will be characterized by the low resistivity. So in the resistive logging tool, whenever the record is taken against shelly formation, which is made of 60% clay, they will show you low resistivity. Overall, if we talk about resistivity of the porous sedimentary reservoir formation, such as sandstone, cormorant, or dolomite or limestone, so reservoir rock resistivity depend upon its porosity, saturation. So now this concept will be used when we are interpreting the resistivity of data. Moving on, what are the some typical values of resistivity of reading? For example, resistivity values can range from 0.5 ohm to 1000 ohm meter depending upon type of formation and also porosity and saturation values. For example, such as sands generally may record resistivity in between the 0.5 to 50 ohm meter or higher depending upon the porosity and saturation of fluids. Cormorant generally show high resistivity. Because the carbonate, most of the porosity in form of secondary porosity, they might be concentrated in certain spaces. So there, it could be that argued that tortuosity might increase compared to the sandstone bearing formation. Evaporite deposits, they have resistivity in several thousands. Formation water resistivity ranges from few hundred of an ohm meter. So, it will, for example, values such as 0.022, 0.2, these are common values. And but if it is fresh water bearing formation, resistivity could be very high, even in hundreds and thousands also. For instance, seawater have resistivity of 0.35 ohm meter. So that is, you can see, you can expect the, since the formation water is generally considered to be saline, or most of the water bearing formation associated with the oil bearing formation or gas bearing formation, you will see the saline formation water is present. So they will have resistivity somewhere in very low values in this range. Now, what are some primary applications? So ratio logging tool can be used to distinguish between hydrocarbon bearing formation with water bearing formation. It can indicate permeable zone. It can determine the water and hydrocarbon saturation. For example, in earlier figure, the first application is to differentiate between the hydrocarbon bearing formation and water bearing formation. As I mentioned earlier, in water bearing formation, where the saturation is 100%, it will have low resistivity, and where saturation is in less than 100%, in oil bearing formation, we will have high resistivity. So whenever you see high resistivity, that is indication of, it's a just indication, it's not 100% confirm. We have to confirm with the other log, but it is an indication or a clue about formation being saturated with oil. Resistivity is low, that is indication of formation being saturated with formation water at 100% saturation or the presence of a water bearing formation. You can see like this two, like in the here, this two could be cell formation, which also characterized by the low resistivity value. So water bearing formation and cell both can have so low resistivity values, but cell could be easily distinguished from a water bearing formation in gamma ray log and density and neutron log. So although from the resistivity log values, you may not be able to say that whether it is a water bearing formation, this one or this one is water bearing formation, but you can easily classify with the help of other law. So, and next quantity application would be the first quality application to differentiate between the oil bearing formation and water bearing formation. Quantity application would be to calculate the water saturation. For example, water saturation can be calculated using Archie equation, where A is the totality factor or empirical factor, N is saturation exponent, M is cementation exponent, Phi is the porosity, RW is the formation water resistivity, and RT is the deep or true resistivity. So RT data will come from our ratio log data. Phi data will come from the porosity data, such as sonic density or a combination of any other neutron density or any other law combination. A, M, and N, these are the empirical parameters which are generally derived from the laboratory data. So, for example, if we consider the two fundamental equations, formation resistivity factor and resistivity index, where F is equal to R by RW and F is related to porosity H, A divided by phi for M, where M is the cementation factor, and I is RT by RO, or 1 divided by HW power N, where N is the saturation exponent. These two equations F and N is combined in this equation to calculate the formation water saturation. This is the equation which is derived by combining F and I. So simply put the value of ROH F RW or ROH A divided by pi for M into RW into this equation to calculate the water saturation equation. Now, what is the value of A, M, and N? So it depends upon what type of rock it is and the degree of cementation. For example, start with the parameter value M. The M value could range anywhere between, let's say, 1.5 to 4 or slightly higher also. For sandstone rock, it could be different. For carbonate rock, it could be different. For example, for sandstone rock, depending on degree of cementation, for example, very loose sand we have value of m around 1.2, 1.3. We have unconsolidated reservoir rocks formation where its value could be 1.3 to 1.5. As the degree of cementation increases, the value could be increased when greater than 2. Generally, we take the value of m is equal to 2. So consolidated sandstones, then we will have value range between 1.8 to 2. For carbonate rock, value of m is generally higher because of the reason that porosity is mainly in form of secondary porosities, and it might be concentrated in terms of bulks and moles. So there the value of M generally higher as compared to the sandstone bearing formation. So values in the range of 1.7 to 4 have been observed for different type of rock. Value of A, it could be 0.5 to 5. It is a tortuosity factor or empirical factor, and its saturation factor, its value can range from 1.8 to 4. Again, it will depend upon the rock type and such as the wettability characteristic of the reservoir rock, whether it is a rock is water weight or oil weight. Now, A we can generally take 1 and generally we can take 2. So A value of A is equal to 1, M is equal to 2, and N is equal to is very common. But these set of values are most common generally for a carbonate rock. So if nothing is even given to you, it's not known to you, and it's a new well, new reservoir, and you have not done the core analysis, which could be used to calculate these parameters. If you want to have a preliminary estimation of saturation, you can take the value of A is equal to 1, M is equal to 2, or N is equal to 2. Otherwise, what we should do is that we should have laboratory investigation. For example, by analyzing the data of a number of core sample, we can determine the value of A and M in the laboratory. So F is given as R by RW or A into 1 by 5 to the power M, where the 5 is the porosity. So I take log of both sided, log of F will become what? Log of A minus M log 5. So we can plot log of F and log of 5. So a plot between the formation resistive factor log F and the log of porosity log of 5 will give you a straight line which intercept this and slope of M. So from here directly value of A could be written from the graph, and from slope we can determine the value. So like in this figure I have mentioned A is equal to 1 or M is equal to 2, that is the generally common values, reference value that is for A and M. But if value is something different, we can also determine from this plot. So for what you need to do is that you need to take a number of core samples from the well and calculate the formation resistive factor and the property from those core data, and then plot them like this to calculate the value of A and M. So in order to calculate number of data regarding formation resistive factor, what we need the value of RO and RW. So you also must have a formation water sample whose ratio is RW. So if formation water sample representative of the actual water inside the formation must be used while saturating the core. So number of core could be saturated to calculate the RO values. So for different cores, that's for you have different cores, let's say core 1, 2, 3, 4, and so on. You can calculate the value of F, F1, F2, F3, F4, and then calculate the porosity values also, phi 1, phi 2, phi 3, and so on. And then you can do this plotting to calculate the values of E and M. Similarly, you can also calculate the saturation exponent and using the resistivity index equation. For example, if I take a log of that, it will become a log of I is what? Minus n log of SW. So you will again have a straight line with slope of minus n. So you can take a different number of core sample. You can vary them on the basis of water saturation. That means you can at different water saturations, you can calculate the value of I. So for different water saturation, calculate the value of I and plot. So you can use also a number of core sample, or a single core sample could be saturated with different water saturation values. So in a zone where you want to calculate water saturation exponent, we'll take the core sample, number of core sample from that zone, and then try to calculate in the laboratory what are the resistivity index values, at different saturation. So now to calculate resistivity index values, you need to write what RT values and RO values. That means for each rock, you must calculate RO, that is the resistivity of the rock that at 100% water saturation, and then you also need to calculate RT at different saturation values. So once we have that, you can plot them together and you get the value of N from this crosstalk. So these equations will be using to calculate the water saturation from the our ratio log data. So now we have discussed what are some some of application of our ratio log. Now we move on to the different types of logging tools and what do we record. These are the some ratio logging tool examples: normal log, lateral log, macro lateral log, proximity log, induction log. These are some generic tool name. Different service companies or logging companies might have different tools. Might have different name, but the principle of those logging tools are same. How they going to measure the resistivity? So basically, for example, a current-based electrologging tool, they are going to measure the resistivity by sending a current inside the formation and then measuring the potential difference. Now, what is the difference between all those logging tools is they measure different type of resistivity. We already know that we have a flush zone in the rock, then we have a transition, and then we have a true zone in the rock. So flush zone measure our flush zone resistivity Archie. So if a tool which is designed to investigate, which have very small depth of investigation, that means it can only investigate, you can see here in this region, it will measure the flush zone resistivity. For example, two logging tools such as one is SFL, you can see that is the blue lines, blue circle. It shows that what is the depth of investigation of SFL logging tool, that is strictly focused logging tool. Second is the micro SFL logging tool, that is micro strictly focused logging tool, which have very small depth of investigation. You can see these two logging tools, they can only investigate in this area. That means they will be measuring only the flush zone resistivity Archie. If a tool which have, let's say, depth of investigation such as like this, that's yellow curve, it is going to measure the resistivity from, can say, from here to here, flush zone and the average of transition zone resistivity. Similarly, if a tool which is having very large depth of investigation, for example, the green area, it is going to measure the proof formation resistivity RT values. So these logging tools can be defined on the basis of our depth of investigation, what type of resistivity they are measuring, whether they are going to investigate the proof formation or they are going to investigate only in the flush zone or in the transition zone. For example, if you see what is the typical depth of investigation, the deep pressure logging tool, which is going to measure the true formation resistivity, they generally have depth of investigation of 4 feet or higher. In many books, you will see some example with name as LLD, that is nothing but D stands for deep measurement. LLS, that means S stands for shallow measurement, or the medium resistivity, which have a depth of investigation around 2 feet. Shallow resistivity, which have few inches, which is going to measure the Archie value. Before we move on to the tool part, what are different types of logging tool, I just want to mention few qualitative points also, so that you understand when the tool record any particular resistivity value, what the resistivity value could mean. Now, since we have already discussed that we have three types of ratio logging: deep, medium, and shallow. So the deep is going to measure the true resistivity, medium is going to measure the transition zone resistivity, and shallow ratio logging tool is going to measure the flush zone resistivity. So if a deep resistivity value is high, obviously that is indication of oil bearing formation. Again, this could be another case also when you have tight formation also. That means tight formation means what? When you have very less porosity. The tight formation have very less porosity. That means pore volume is low. If the pore volume is low, that means amount of formation water will be very low. So even if, let's say, tight formation, which is a water bearing formation. So water bearing formation means what? 100% water saturation. But it is tight formation, low porosity formation. it have low pore volume. Thus, even at 100% formation water saturation, it will have a very very low amount of formation water or low ions to conduct electricity. Thus, it will have very very high resistivity also. So this could be easily identified with the high resistivity due to the presence of oil or low porosity in our density, porosity and neutron porosity log data. That's why we always need to correlate all the logs together. Just by looking at the single log, let's say for example resistivity logs, but just on the basis resistivity log value, we cannot indicate that this is a hydrocarbon bearing formation because my RT is very high. I must check also where RT is high, what is my porosity logs are saying. If only porosity logs are saying, that means I have what? I have, it is a hydrocarbon bearing formation. Similarly, deep resistivity, if you have low value, that means our RT is low value. That means I have what? A water bearing formation. Once again, I can also confirm with the help of also my porosity data, such as density data or neutron logging data to confirm that. I should also have very good porosity also. Suppression between resistivity values. This is again indication of porous and permeable formation and the mud filtered being different from the formation fluid. Since these deep, medium, shallow resistivity logging tool can measure the RT values, RX values, or the RI values. And we know that in the early lecture we have discussed RX value will be different, RT value will be different, and RI value will be different. So that means the three types of resistivity logging tool which are going to measure the three types of resistivity will measure three different resistivity values. So if you see in this figure here, this is the first one is, it is deep resistivity, it is RT value. It is medium resistivity, this is RI values. This is shallow resistivity value, this is RX values. Same here also, RT, RI, and RX. So there is separation. You can see in the oil bearing section and water bearing section there is separation. This is indication of a porous and permeable formation. If the rock is totally impermeable, what will happen? The mud filtration cannot happen because it will not allow the fluid to flow inside. And we know that this value will differ only when RMF is not equal to RW. For example, in water bearing formation, we have discussed that in water bearing formation, we will get only difference between the values between RT and RI and RX values when the RMF is not equal to RW. An example of this we discussed in the last lecture. So this separation between value indicate that we are dealing through a porous and permeable formation where the invasion can happen and the mud filtrate is different from the formation fluid. So if you do not get a separation, that it does not mean that it is not indication of a porous and permeable or hydrocarbon bearing formation. The separation could not be there because mud filtrate and the formation water are same. This you need to keep in mind. For example, this is a water zone when RMF is equal to, sorry, RMF is greater than 3 RW. That means mud filtrate is highly resistive compared to the formation water. You can see in the water bearing formation we are getting separation. This is our RT values, this is our RI values, and this is our RX value. You can see the RX values are higher as we discussed in the last lecture. When the RMF is greater than RW, RX value will be higher and RT value will be lower. But that is a true formation resistivity, that is water bearing formation resistivity, which is completely such with the formation water. Where RX is the mud filtrate, affected by a mud filtrate invasion in the flush zone. The flush zone we have what? 100% mud filtrate. That's why it has higher resistivity. But in the next example, you can see when RMF is equal to RW, even in a water bearing formation, what we have, there is no separation. Everywhere it is same. That it is reading same value. That means it is water bearing formation, but mud filtered is same as the formation water. Both have the same property. You can see also in the oil bearing formation, separation will still be there across the oil zone, but separation value might be slightly lesser than the, as it is more pronounced in water bearing zone, because now we have oil in the flush zone as well in the true formation. So today we have discussed about the fundamental of ratio log, what does the ratio log record, what are the different values it can record, such as deep, medium, and shallow resistivity, what is the significance of RT, RI, and RX values, and how true formation resistivity RT value could be used. In next lecture, we will start discussion on different type of logging tool. So I've introduced you with few logging tool example. So in the next class, we'll start with first normal log and lateral log. Then we move on to the other type of logging tool. See you in the next lecture.